Hello students, welcome to the lecture on Advanced Linear Programming, and after this lecture we will be able to learn the following objectives. Discuss the revised Simplex method, explain the bounded variables algorithm, discuss the parametric linear programming. Let us start with the advanced linear programming. Linear programming is a generalization of linear algebra. It is capable of handling a variety of problems ranging from finding schedules for airlines or movies in a theater to distributing oil from refineries to markets. Linear programming has long proved its merit as a significant model of numerous allocation problems and economic phenomena. The continuously expanding literature of applications repeatedly demonstrates the importance of linear programming as a general framework for problem formulation. The fundamental theorem of linear programming. Through the fundamental theorem of linear programming, we establish the primary importance of basic feasible solutions in solving linear programs. The method of proof of the theorem is in many respects as important as the result itself, since it represents the beginning of the development of Simplex method. The theorem itself shows that it is necessary only to consider basic feasible solutions when seeking an optimal solution to a linear program, because the optimal value is always achieved at such a solution. Linear programming was developed as a discipline in the 1940s, motivated initially by the need to solve complex planning problems in wartime operations.
Hello, this is Mr. T with a tutorial on linear programming. The purpose of linear programming is to optimize a function. Optimize means to either maximize or minimize that particular function. In this case, though, that function is subject to a set of constraints that limit the particular values for x and y that we can choose. These constraints are usually provided as a system of inequalities. In the last lesson, we learned how to graph systems of inequalities to find the solution space. Linear programming was invented during the World War II by mathematicians to support the war effort, and they came up with methods to optimize the amount of cargo that they could load on ships and planes. This technique was kept secret during the war because we didn't want that to get to our enemies. After the war, it was published and has been adopted by many large corporations for managing their resources. When we graph the system of inequalities that form the constraints, they form usually a closed-in space, which I've shown in the diagram here. Over here, we've shown the diagram. So we had four inequalities here, a vertical line, a horizontal line, and these two lines here. And they formed a solution space, which is called the feasible region. So when we are trying to optimize the objective function, we could pick any point in the feasible region as well as the points along the boundaries. As you can see, if we wanted to check all the points in the feasible region, it would be impossible because there's an infinite number of points. However, the concept of linear programming says that the maximum and minimum values for the objective function will occur at the corners or the vertices. So we only have to check a point. We only have to check points at each of the corners of the vertices. So we can find the x and y coordinates of the vertices and substitute those into our objective function and decide which one provides the max and the min. So we have here an example. We have an objective function. At this point we don't know what that stands for. Maybe it's profit or something. And the function is determined to be 5x minus 3y. There was a system of inequalities that were graphed to form this feasible region, all the possible solutions, and we're supposed to find the optimum values. So remember, our optimum values will be at the vertices. So this vertice, the coordinates are 0, 2. This vertice, the coordinates are 3, 4. At this vertice, our coordinates are 6, 2. And at this vertice, our coordinates are 0, -2. The easiest way is to form a table where we input our x, our y values, and we then compute our objective function for each of those. So if we fill in our table, we have 0, 2, 3, 4 going around the diagram, 6, 2, and 0, -2. So now we can calculate p by substituting in. So here we have 5 times 0 minus 3 times 2, we get -6. Here we have 5 times 3 minus 3 times 4. That's 15 minus 12, we get 3. Here we have 5 times 6 minus 3 times 2. 30 minus 6 is 24. And finally, 5 times 0 minus 3 times -2 is a +6. Now we can compare our p-values and find the max and min. Here we see we have a minimum and the maximum. So for our function, we have the minimum is -6 at the point 0, 2, and maximum is 24 at 6, 2. Hope this helps.
Now we will discuss about the revised simplex method. Revised simplex method is an improvement over simplex method. Revised simplex method is computationally more efficient and accurate. Duality of LP program is useful property that makes the problem easier in some cases and leads to dual simplex method. This is also helpful in sensitivity or post-optimality analysis of decision variables. Benefit of revised simplex method is clearly comprehended in case of large LP problems. In simplex method, the entire simplex tableau is updated while a small part of it is used. The revised simplex method uses exactly the same steps as those in simplex method. The only difference occurs in the details of computing the entering variables and departing variable. Let us consider the following LP problem with general notations after transforming it to its standard form and incorporating all required slack, surplus and artificial variables. As the revised simplex method is mostly beneficial for large LP problems. Arithmetic complexity. The arithmetic complexity of an algorithm is the number of additions, subtractions, multiplications, divisions and comparisons performed in a full run of the algorithm. The arithmetic complexity is a reasonable measure of the amount of time a computer will take to run the algorithm, provided that there is not much else going on in the algorithm besides basic arithmetic, and provided that the size of the numbers involved is bounded. The arithmetic complexity of matrix operations and pivoting. Let A be an M cross n matrix. Then a row operation takes at most 2n arithmetic operations, since as multiplying a row of A by non-zero scalar takes n multiplications. Adding a multiple of a row to another row of A takes n multiplications and n additions. A pivoting operation on A takes m row operations, so at most 2mn arithmetic operations. Gaussian elimination takes at most rank A pivoting operations on the coincident matrix A to be find a matrix in row echelon form. If A has m rows and n columns, then the arithmetic complexity of Gaussian elimination is at most rank A 2n plus 1 m, or since rank A less than equal to m, at most 2 n plus 1 m2 arithmetic operations. The simplex method is to repeatedly apply pivoting steps on a tableau, which is a block matrix of size m plus 1 multiplying n plus 1, say. To determine the pivot I note, j note takes at most n minus 1 comparisons. For finding j note is equal to minimum j cj greater than 0, then m comparisons and at most m divisions to calculate bi divided by aij note. Aij note is greater than 0, and finally at most m minus 1 comparisons to find the minimizer I note j of this set. The pivot itself will take at most 2 n plus 1 m plus 1 arithmetic operations in all at most n minus 1 plus 3m minus 1 plus 2 n plus 1 m plus 1 arithmetic operations, which is ONM. In practice, this worst case bound is indeed proportional to the amount of time needed. The simplex method would be useless if its average behavior was close to the worst case bound. However, empirical studies show that the number of pivot steps is usually linear in n, the number of columns of the table. The simplex method has been the standard technique for solving a linear program since 1940s. In brief, the simplex method passes from vertex to vertex on the boundary of the feasible polyhedron, repeatedly increasing the objective function until either an optimal solution is found or it is established that no solution exists. In principle, the time required might be an exponential function of the number of variables, and this can happen in some contrived cases. In practice, however, the method is highly efficient, typically requiring a number of steps which is just small multitude of the number of variables. Linear programs in thousands or even millions of variables are routinely solved using the simplex method on modern computers. Efficient, highly sophisticated implementations are available in the form of computer software packages. Modular arithmetic. In mathematics, modular arithmetic is a system of arithmetic for integers.
Hello. Now, this is basically a lecture about modular arithmetic, and I'm going to start with some very basic stuff. So first, as I mentioned last time, what are we talking about when we talk about modulo math? What we're basically doing is math in a circle. So for example, let's look at the numbers 1 through 10. So we can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we have the numbers 1 through 10 arranged in a circle. And when I say we want to do math in a circle, it means we want to think of addition around the circle. So we'll say 0 plus 2 is moving 2 steps away from 0. So that's going from 0, 1, 2 is just 2. And similarly for any addition. So we can do, for example, 4 plus 4 is 4 plus 1, 2, 3, 4 is 8. So far it's the same as regular addition. Where things get interesting is where we have to wrap around the circle a little bit. So if we do 6 plus 6, we get 1, 2, 3, 4, 5, 6 plus 1, 2, 3, 4, 5, 6. We get 2. So this is what we get when we're working in mod 10. So addition is pretty simple. Multiplication is the same way. Multiplication, what we do is multiplication means the same as it does before, which is if you have 2 times 2, that's the same as adding 2 to itself twice. So that's 4. And where it gets interesting is where we have something like 3 times 6. So 3 times 6 is adding 6 to itself 3 times, or 3 to itself 6 times. And then we get 6, 6, 6, 8. So this is how multiplication works in Mod 10. And by now, you might have suspected something. 3 times 6 in normal decimal addition that we normally do is 18, and here we just have 8. So this suggests maybe it has something to do with the last digit. So after all, 6 plus 6 is 12, normally for us, and now this time it's going to come out to be 2. Let's try it for something else. Let's say do something big, 7 times 7. So 7 times 7, what's that? Well, 7 times 7 is 49, so we guess that the answer should be 9. Let's see if that's true. We go 7 plus 7 plus 7 plus 7. We keep doing this. We will find, in fact, the answer is 49. So this works pretty well. So what's the trick we've learned? So we do 7 times 7, and we write down 49. And basically, when we take doing math in Mod 10, we just take that 9 as the answer. So what is the rule? Basic rule is like this. If you want to add or multiply mod something, say p, just calculate x plus y normally, and then take the remainder. After dividing by p. So this kind of taking the remainder after dividing by p, what does it have to do with this last digit? Well, it's because, remember, in base 10, we write numbers down in base 10, that last digit, the ones place, that place is basically the remainder after you divide by 10, because everything, all the higher digits are 4 times 10, and out here you could have something times 100. So the basic rule we have for doing multiplication and addition, normally we can just use the same thing, just keep track of what's in the last digit in the appropriate base. So if we're doing mod 10, it's base 10. If you want to think about mod 5, we do it in base 5. Just look at the last digit. So this is basically how the basic arithmetic operations work. Now, to understand this a little bit better, what we should do is to actually write out the entire multiplication and addition table for a particular case.
Here we will discuss about bounded variables algorithm. Many network flow problems involve upper bound constraints, since the flow rate in an arc, that is a pipeline, is usually bounded above. A straightforward method to solve the problem is to absorb the upper bound constraints into the set of functional constraints to form a new problem. The disadvantage of this approach is that the number of constraints in the LP increases with the number of variables, and especially in the old days is computationally expensive. Is it possible to have an algorithm that avoids incorporating the upper bound constraints into the functional set? After all, the standard simplex method has, but the method does not incorporate the non-negativity lower bounds into the set of functional constraints. Indeed, it is possible to spare the upper bound constraints from the set of functional constraints as for the non-negativity lower bounds. The simplex method for bounded variables is such an algorithm. The ideas for the bounded variables are in fact embedded in many network algorithms. Here we introduce the ideas through linear programs and make relevant comments when we encounter the ideas in specific network problems. Complementary slackness conditions. It is a pair of primal and dual linear programs. The optimal solution of the two linear programs can be defined by the complementary slackness conditions. Let us apply the idea to a primal problem with upper bound constraints. The primal problem is as shown on the screen. Let y and alpha be the vectors of dual variables corresponding to ax less than equal to b and the upper bound constraints x less than equal to u respectively. Then the dual problem is as shown on the screen. Extended basic feasible solution. An extended basic feasible solution generalizes the idea of basic feasible solution for linear programs with bounded variables. Suppose that A is an M cross n matrix, M less than equal to n, and of rank M. An extended basic feasible solution of the primal is a feasible solution such that n(m) variables are equal to either their lower bound 0 or their upper bound, and the remaining m variables have linearly independent columns in A. These m variables are called the basic variables. See on screen. Upper bound maximum minimum conditions. An extended basic feasible solution x is minimal. To know more about this, see on the screen. Let's describe the parametric linear programming. The use of parametric linear programming, PLP, adds a new dimension to least cost linear programming. This technique is extremely versatile and in the hands of a creative and imaginative nutritionist can be valuable in many aspects of feed formulation. Some of the areas in which PLP can be used to advantage are planning and formulating diets for experimental purposes, evaluating the potential sales value and usage level of new or improved feeds tufts, determining the economic benefit of improved feed processing techniques, determining costs and benefits of modifications in nutrient requirements. Here we will discuss about parametric programming. This is a technique for investigating the effects of a sequence of proportionate or incremental changes in the elements of a row, column or right-hand side. A selected factor is parameterized, that is, examined at increasing or decreasing increments, and the effect on the least cost solution is examined. Several different parametric procedures can be used in feed formulation. First, the value of the objective function of the solution. In this example, the cost may be varied. This is often called a parametric cost ranging and utilizes the para-OBJ program. The nutrient specifications set forth in the right-hand side section may be varied by the use of Parr's program. This is also known as parametric restriction ranging. The effects of altering the amounts of one or more attributes of a specified feedstuff by the para-col program may be studied, also known as parametric nutrient ranging. The effects of changing values of a specified attribute, such as the available phosphate content, in one or more feedstuffs simultaneously can be studied by the para-rho program. Thus, para-OBJ parameterizes the objective function Par's, parameterizes the right-hand side values, para-col parameterizes one or more elements in a specified column, and para-rho parameterizes one or more elements in a given row. Parametric restriction ranging. This option can be one of the most valuable and powerful formulation tools a nutritionist may have at his disposal. By proper use of this program, one can quickly establish a series of linear changes in his nutritional specifications and examine their effects on the diet composition and costs. The changes may be either positive or negative, that is, the specified level of the nutrient may be increased or decreased. Changes in the level of more than one nutrient at a time may be examined simultaneously with the specified change in each nutrient independent of changes in other nutrients either in direction or magnitude. Parametric column ranging. This option is used to direct the parametric ranging of elements within a specified column. A certain ingredient is selected, only one ingredient at a time can be considered. 1. Several, all of the row values within this column may be increased or decreased. It is often possible to change the nutritive value of an ingredient by some processing method, enzyme addition, etc. with some control on the degree of change. The Paracol program, therefore, can be very valuable in determining the economic feasibility of ingredient processing and suggests possible areas of research on factors known to influence the nutritive value of an ingredient. Parametric row ranging. The para-row option is similar in setup and operation to the other parametric operations. In this program, a specific row is selected and the value of this row in one or more feedstuffs is altered by a specified amount. Parametric cost ranging. Parametric cost ranging involves changing the value of the objective row cost in the model for a specified ingredient while the price of other ingredients remains constant. While it is technically possible to range the price of several ingredients simultaneously, it would be difficult to interpret the output. The data output or solutions of the para-OBJ program will trace the usage level of the selected ingredient at different cost levels. The usage level will generally be a step-like function rather than a straight line, with the width and height of the steps varying in relation to the competition from other feedstuffs. Here we will discuss about parametric variations in objective function. One of the most challenging of guidance and control problems is that of a modern tactical air-to-air missile in pursuit of highly maneuverable aircraft. The missile, in an attempt to intercept the aircraft, undergoes dramatic changes in flight conditions and experiences high accelerations capable of exciting a multitude of unmodeled high-frequency dynamics. The parametric variations associated with these changes in flight conditions and the possible excitation of high-frequency unmodeled dynamics can cause the missile's control system to degrade and in many cases to become unstable. Because of this potential for instabilities, the performance one can extract from a missile control system must be offset by the requirement that the closed-loop system remain stable in the presence of model uncertainties and parametric variations. The conflicting requirements between performance and stability have been the focus of much research in the past several years. Now, in the end, let us summarize what we have learnt in this lecture. Linear programming has long proved its merit as a significant model of numerous allocation problems and economic phenomena. Revised Simplex method is an improvement over Simplex method. Revised Simplex method is computationally more efficient and accurate. The arithmetic complexity of an algorithm is the number of additions, subtractions, multiplications, divisions, and comparisons performed in a full run of the algorithm. The Simplex method for bounded variables is such an algorithm. The ideas for the bounded variables are in fact embedded in many network algorithms. This technique is extremely versatile and in the hands of a creative and imaginative nutritionist can be valuable in many aspects of feed formulation.